So hello everyone. Welcome to another episode of Material Matrix. Welcome. Tonight we explore predicting polymer teacher, so crucial for material applications. We'll discuss how machine learning offers faster alternatives, evaluating uncertainty like quantification methods, and key findings for enhancing ML models. This drives innovation and efficient material development. So, can you explain the significance of predicting the glass transition temperature, texture of polymers in material science, and how this relates to their practical applications? So,
predicting the glass transition temperature or to polymers is like knowing when a popsicle will start to melt. Like, just as the popsicle changes from a solid to a gooey mess at a certain temperature, polymers change from a hard and brittle state to a kind of softer, more kind of flexible state when they reach their check. This change is really crucial because it affects how the material behaves in real life applications in material science. So understanding TEACH helps scientists and engineers decide how to use polymers in different products. For example, if a polymer is used in a medical device, it needs to stay firm at body temperature, but might need to be flexible for comfort. Similarly, in aerospace engineering, materials must withstand extreme temperatures while maintaining their strength and flexibility. So traditional methods to find TEACH out can be slow and expensive, so much like baking a cake from scratch. However, using machine learning is like having a magic oven that can tell you when your cake is like perfectly baked without all the lighting. Machine learning allows for faster and cheaper predictions of TEACH, making it easier to design new materials that meet specific needs across various industries. So this can lead to better products and innovations, ultimately benefiting everyone. So,
in the context of using machine learning for predicting TEACH, what are the specific uncertainty quantification UQ methods evaluated in the study, and how do they differ in terms of their approach to handling uncertainty in model predictions? So
in the context of using machine learning to predict the glass transition temperature, TEACH of polymers, 6 different uncertainty quantification, so UQ methods were evaluated. Think of these methods as different tools in a toolbox, each designed to actually tackle the problem of uncertainty in its own way. One, Monte Carlo-based methods. These methods, like ensemble models and Monte Carlo dropout, work by taking so many random samples to see how predictions can vary. Imagine rolling a dice multiple times to see just how often you get each number. This helps estimate how uncertain the predictions are by showing the whole range of possible outcomes. Architecture-specific methods like these include evidential deep learning, ELR, and mean variance estimation, IP. These methods are built right into the design of the model, like having a built-in thermometer in an oven that tells you the temperature. So they calculate uncertainty metrics such as averages and variations alongside making predictions, which makes them really efficient during both training and evaluation. 3. Bayesian methods, examples are Gaussian process regression, so GPR and Bayesian neural networks blend in. These methods take a probabilistic approach, meaning they consider the uncertainty in the predictions more deeply. It's like not just guessing the temperature of a cake, but also thinking about how certain you are about that guess. They provide a broader view of uncertainty by addressing the limitations of single model predictions. So each of these methods has its kind of strengths and weaknesses. Some may require more computational power, like just needing a bigger oven to bake more cakes at once, while others are designed to be more efficient and integrated into the model itself. So, by evaluating these different methods, researchers can choose the best one for accurately predicting KIK and understanding the uncertainties involved. So,
how did the study assess the performance of these UQ methods, particularly in terms of metrics like Spearman's quote, rank correlation, calibration, and sparsification, and what kind of insights were gained from these evaluations?
The study assessed the performance of the uncertainty quantification UQ methods using several metrics like Spearman's rank correlation, calibration, and sparsification. Each of these metrics helps to understand how well the models predict uncertainties and how those relate to actual prediction errors. So what Spearman's rank correlation like this metric measures how well the predicted uncertainties align with the actual errors. A higher value indicates a stronger relationship. In this study, the Bayesian neural network, Braun and Monte Carlo dropout McDonough methods showed a pretty modest correlation, suggesting that when these models predict higher uncertainty, it often corresponds to larger errors. In contrast, other methods like Gaussian process, like regression, like GPR, and evidential deep learning, et al. Had very low correlations indicating that their uncertainty predictions did not effectively relate to actual errors. Calibration analysis checks how confident the models are about their predictions. So, ideally, if a model predicts a certain level of uncertainty, it should be corrected so often. The study found that all 6 UQ methods were overconfident, meaning they often predicted uncertainties that were not aligned with reality. However, GPR just stood out by maintaining higher accuracy, suggesting it was better at making reliable predictions, even if it was still overconfident. For sparsification, this metric looks like at how the error changes when uncertain predictions are removed. It helps to identify if eliminating less certain predictions can improve overall accuracy. So, the study evaluated how the root mean square error was changed with the removal of these uncertain predictions, providing insights into the impact of uncertainty on prediction performance. From these evaluations, the study revealed that while some methods showed promise in correlating uncertainty with actual errors, others struggle. So the insights gained emphasized the importance of selecting the right UQ method for reliable predictions, as well as the need for further refinement to improve the calibration and reliability of all methods tested.
So what were the key findings regarding the impact of excluding data points with high uncertainties on prediction accuracy, and how might these findings influence the approach to data-driven polymer design?
So the key findings regarding the impact of excluding data points with high uncertainties on prediction accuracy revealed that removing these uncertain predictions led to reduced errors in the models like outputs. So this suggests that by focusing on more reliable data, the accuracy of predictions can be improved. Think of it like trying to bake a cake. If you remove the ingredients that are not fresh or reliable, you're more likely to end up with a really delicious cake. However, the study also highlighted a challenge like the prediction accuracy for polymers with high glass transition temperatures. Taxi remained low. So this was primarily due to a lack of sufficient high-TIG data in the training sets. So, without enough examples of these high-TIG polymers, the models really struggle to learn how to predict their properties accurately. These findings could pretty significantly influence the approach to data-driven polymer design. So the insights suggest that researchers should focus on gathering more data on high-TIG polymers, either through experiments or simulation. By expanding the training dataset to include a wider variety of these materials, so models could be better trained to recognize patterns and make more accurate predictions. So this would ultimately enhance the design of new polymers with desirable properties, leading to innovations in various applications.
In light of the findings regarding UQ methods and their effectiveness, so what kind of recommendations does the study provide for enhancing the robustness of machine learning models in predicting TG, particularly in the context of future research and development?
The study provides several recommendations for enhancing the robustness of machine learning models in predicting the glass transition temperature, TG of polymers, particularly in the context of future research and development, and sort of incorporate uncertainty, quantification, UQ methods. Utilizing UQ methods is essential for improving the reliability of predictions. These methods can help refine the selection of candidates for the training set, ensuring that the models are trained on data that is both relevant and really informative. This active learning approach enhances the model's robustness and stability. To focus on active learning techniques, active learning allows models to selectively identify and learn from the most informative data points. So by focusing on these key data points, researchers can improve the model's performance without needing to gather vast amounts of data, which can be time-consuming and really costly. 3. Enhance data diversity. Expanding the training data set to include a broader range of polymer types, particularly those with high TGL, is so crucial. This diversity will help the models learn better and make more accurate predictions, so leading to improved design outcomes. 4. Optimize computational efficiency. While methods like Gaussian process regression, GPR are effective, so they can be computationally extensive. So future research should aim to optimize these models to reduce computational costs while maintaining their predictive power. This could involve exploring faster algorithms or more efficient training processes. 5. Ensured interpretability. Providing interpretability in model predictions is vital, especially in high-stakes applications where safety and reliability are really important. Enhancing the interpretability of UQ methods can help users understand the decision-making process of the models, leading to better trust and informed decision-making. So by following these recommendations, researchers can actually improve the effectiveness of machine learning models in predicting TGR, ultimately advancing the field of polymer design and leading to safer and more reliable materials.
How do the insights actually gained from this study inform the broader implications for data-driven approaches in materials science, particularly for the development of new materials and innovations across various industries?
The insights gained from this study have pretty significant implications for data-driven approaches in material science, especially in the development of new materials and innovations across various industries. Here are some key points like 1. Efficiency and material property prediction. Experimentally measuring the properties of materials can be very resource intensive, similar to just having to bake each cake from scratch to find the best recipe. Machine learning ML offers a more efficient alternative by predicting these properties using existing data, which can actually save time and resources. This efficiency is so crucial for rapid material development. 2. Importance of confidence levels, like the reliability of predictions for new polymer candidates, depends on the confidence levels provided by ML model. This is kind of like having a weather forecast that not only predicts rain, but also tells you how confident they are in that prediction. High confidence helps researchers decide whether to move forward with experimental validation, ensuring that resources are not so wasted on unlikely candidates. 3. Role of uncertainty quantification. So UQ is essential for enhancing the reliability of predictions. By incorporating UQ, researchers can better navigate the chemical space for polymer discovery, ensuring that new materials are viable before they undergo costly experimental testing. So, this is akin to having a map that helps you find the best routes, instead of just wandering aimlessly. 4. Generalization capability of ML models. The ability of ML models to generalize to new, out-of-distribution data is so critical. So this means that models should be able to predict properties of materials that were not included in the training dataset. Improving this capability ensures that new and innovative materials can be identified and developed, so even if they differ significantly from existing materials. 5. Addressing data limitations. The study highlights the challenge of low accuracy in predicting high TG polymers due to insufficient training data. So, this really points to the need for future research to focus on expanding datasets, which will ultimately lead to better predictions and more innovative materials. Overall, these insights suggest that a robust and reliable data-driven approach, supported by effective UQ methods, can really facilitate the discovery and design of new materials. This could lead to advancements across various industries, like from healthcare to aerospace, where innovative materials can have a transformative impact.
So thank you for joining us today. It's really been an incredibly insightful discussion into the fascinating world of polymer science. We've explored the immense significance of accurately predicting the glass transition temperature, or TGO, of polymers. Like, this is just a theoretical concept. It's absolutely crucial for how materials perform in real-world applications. So from life-saving medical devices to cutting-edge aerospace components. While traditional methods for T-sheet prediction can be both time-consuming and expensive, so we've seen how machine learning is stepping up, offering faster, more efficient, and potentially more accessible alternatives. A really core focus of our conversation was on the critical role of uncertainty, quantification method. So we learned about the evaluation of various approaches, including Monte Carlo-based architecture-specific and Bayesian techniques, and how metrics like Spearman's rank correlation and calibration were used to gauge their effectiveness in handling prediction uncertainties. A key takeaway is that by intelligently managing these uncertainties, even by excluding data points with high predicted uncertainty, so we can significantly enhance prediction accuracy. This also brought to light the challenge posed by insufficient high-TGO data, a crucial area for future work. So looking ahead, the recommendations for advancing ML models in this field are clear: integrating robust uncertainty quantification, embracing active learning strategies, diversifying training datasets, optimizing for computational efficiency, and always ensuring interpretability. So ultimately, today's discussion underscores the transformative power of robust, data-driven approaches in material science. These innovations are not just about making prediction. They're about accelerating the development of novel materials, optimizing design outcomes, and managing resources more effectively across a multitude of industries. So, thank you once again for tuning in. So we look forward to having you join us next time for another deep dive into the frontiers of science and technology.